everyone. How's it going? And welcome to Community Conversations. This is an opportunity for you, the community, to hear from contributors in the internet computer ecosystem, as well as ask them questions live. So today we have Research Manager Björn Tackmann, who will go over the design of the internet identity. I will pass things over to Björn to explain more.
Thank you, Liz. Let me share my screen so that you can see my slides. So the format of today's presentation is a bit more in line of the talks we did for the Genesis event. And the reason is that we actually did not explain internet identity in that event. The reason for that is mostly timing. We explained some of the fundamental building blocks that we're using, like certified variables or ingress message authentication. But we built internet identity rather late in the process, so we didn't manage to make a full presentation on that. So that's what I want to do today. It's going to be high level. It's going to be explaining the whys and the hows, hopefully in a convincing way. But it's not really going to dive deeply. And if you want deep dives on any particular subject, maybe protocol, like cryptographic protocol, or maybe the way we build and deploy things, or maybe user stories, or whatever you come up with, I guess we'd be happy to do follow-up sessions going more into detail. And I guess Liz would be happy to collect your ideas and suggestions. So internet identity is built as an authentication system that works in a decentralized protocol and is built on the internet computer. Now, what is specific about the internet computer is that it serves web content directly from Canister smart contracts running on the blockchain. So that's different from the traditional web, because the software we're running is actually in smart contracts in the canisters, and that's running in a decentralized system instead of one centralized server that may just be replicated for means of crash resilience. And it's different from other blockchains in that we're actually serving the web content directly from the blockchain. And that introduces a somewhat tricky case here for the authentication, because we can't just be building on the traditional mechanisms. But on the other hand, we need to be user-friendly. Users expect to experience the internet computer just from their browser, and it needs to be both secure and user-friendly using a standard browser. But before I explain what exactly we're doing, let me quickly go over why we can't just be using techniques that we've been using in the last decades on the traditional web. So this is a form, it's taken from an academic conference actually, where I logged into the conference system. And as you're probably used to, I did that by specifying my username, here my Dfinity email address, and my password. And that has worked okay. I mean, passwords do have some inherent challenges, which is they should be pretty random, right? So that no one can guess them. You should also not reuse passwords across multiple sites. You might want to update them on a somewhat regular basis. And that, I mean, initially it sounds attractive, right? You just enter username and password, but that gets pretty quickly, it gets a lot too many passwords for my tiny brain, which means managing all these passwords is actually kind of tricky. And at least I'm using software. So my password manager showed me that I have more than 250 passwords. No way I could keep them in my memory. But passwords do have more fundamental problems also in a technical sense of validating the user's authentication request in the platform, which is the platform needs to store the password in some way or form. And while for like 3 decades, we're not storing passwords in plain text anymore, we're usually storing some kind of salted hash. That still means that if someone gets their hands on such a password database, they can still brute force passwords. And as passwords usually don't have great entropy, if you use a proper password manager, maybe okay. But if you're still manually remembering passwords, probably they don't have a great amount of entropy. And in many cases, just running a brute force attack on such a password database will reveal quite a number of passwords. And the second one is that even if the passwords are stored in such a salted hash form, meaning not in clear text, they're usually sent to the server in clear text. And actually, you can, in most like currently used protocols, it's required that either they are stored in plain text, then you may not need to transmit the plain text, or you transmit the plain text and then you can store it in this salted hash way. But if you think about the decentralized platform, we decentralize the internet computer so that individual nodes can be malicious. Now, if we give the password in clear text to a malicious node, either by sending it to it or by storing it on the malicious node, that's not really a great idea, right? That's giving it directly to a potential attacker. So using a password on the internet computer would just not be a good idea. And actually, if there's one thing, if you're building on the internet computer and there's one thing you want to remember from today's talk is don't use passwords. Now, the first thing that's problematic is the password itself, but also other mechanisms that are related to passwords actually don't really work. Like if you think about this reset password link, which would usually create some random number and send you an email, and then you'll have to go back to the website and enter the random number. That doesn't really work because this scheme is very much dependent on this random number being secret and only known to you. Whereas we wouldn't be able to generate this random number and send in an unencrypted email to your mailbox without leaking the password to a potentially malicious node. So there's actually multiple of these mechanisms that don't really work on the internet computer that have been used on the public web, like on the traditional web. But if we're using software to manage our passwords anyway, at least I'm doing that, then why do we stick with passwords anyway, right? For a computer, there's not a lot of difference in storing the low entropy from a password and the high entropy from an actual cryptographic key. So what we're building on in authentication on the internet computer is, of course, proper cryptography. And not surprising, it's going to be digital signature schemes, or it is digital signature schemes. Now, traditionally, they described as consisting of 3 algorithms, one being for key generation, which actually creates a key pair of a private key and a public key. And then there's a second algorithm, which takes a message that you want to authenticate and the private key to generate a signature. And a third algorithm, which takes the message, the signature, and the public key, and that validates whether the signature is actually valid for that pair of message and public key. And what's important here is that the verification does not use any secret state. The verification is only based on the message, the signature, and the public key. And this is a huge advantage over storing or receiving plain text passwords, which we would need to do with typical traditional web techniques, because we can safely execute this verification mechanism also on untrusted, potentially malicious nodes. So if digital signatures are so great, why aren't we using them everywhere, right? They have been invented in the 1970s. We have pretty efficient implementations since late 70s, early 80s. Why aren't we using them anywhere? Well, first of all, there's 3 places where we actually use them. The first one may be known if you're doing a lot of programming or of system administration, which is SSH. SSH public key authentication is probably the most prominent use of digital signatures on the user side. Oh, by the way, I should have mentioned, we are using them a lot on the server side. Like the entire public key infrastructure is built on digital signatures. It's just we haven't been using them a lot on the user side. And then TLS, which underlies like the HTTPS protocol, for example, it also supports public key authentication based on digital signatures. It's hardly used anywhere, but it is supported. And it seems some bigger organizations are actually using that internally. And the third one, of course, is everything related to blockchain. Every blockchain does have some digital signature-based mechanism for keeping the user's funds, for keeping the user's coins secure. And how are we doing in terms of managing digital signature keys? Well, it has a kind of mixed history. It's actually not that easy to keep these keys. First of all, we don't want to leak those keys, right? There's stories like the one on the lower right here, where someone had Ether and they just got hacked and someone stole their secret key, and so it was exposed and gone. But also, in most of the other cases, it's actually not an attacker getting access to the key. It's the security mechanism that we're using to keep the key secure, kind of being too hard to use for the users. So people keeping their keys on an encrypted hard drive and then losing the password, or people like deleting the keys by accident. So there's two major problems we have to solve. The first one is keeping the key only to us, and the second one is actually keeping it to us so that we can also use it in the future. Now, if things are so difficult with these cryptographic keys, why would we think that it's a good idea to have all users of the internet computer actually use cryptographic keys? And the answer is that there has been some recent advances in the Web3C standardizing web authentication. Web authentication is a mechanism that is widely used, especially for two-factor or second-factor authentication. So when you log in with a username and a password, but you also want something that you have, like your device, as an additional measure to protect your account. And that comes in different shapes and forms. On the left-hand side, I've shown a USB key version of that. There's some big manufacturers building those. In the middle is a laptop that has a built-in TPM security chip. On the right-hand side is a phone that have such a built-in chip. So there are multiple devices that actually support this standard by now. And what is important here is that all these devices have a security boundary between where they keep the private key and the device itself. So for example, the USB key will never, ever send the private key over the USB connection. The only thing it's going to do is it's going to create digital signatures on that device and send them back. And it has some other functionalities which we don't care about. And same for the laptop and the phone. They have secure chips which are never going to let go of the private keys. So they're never going to send those private keys to any other part of the computer, not the operating system, not any other chip, nowhere. And that's the important part here. So these chips make sure that the users do not accidentally leak their keys due to anything like a phishing attack or something like that. And it also gives us one other advantage. While it's pretty hard to explain to end users how they should be keeping their cryptographic keys secure, because they usually don't really understand the security properties they would need to keep for those keys, it's kind of easy to tell them, oh, look, here's your device. Your device has been authorized for accessing a certain service. Do you want to use your authorized device to maybe authorize another device? So it's a lot easier for users to think in terms of these devices, like tangible things they can keep in their hands and play with. It's a lot easier than explaining abstract objects such as cryptographic keys. So this is why internet identity is built to a large part on web authentication. There's one more thing I want to go to, which has been an approach by some big tech companies toward improving the user experience in managing their logins. Because as I said before, you're likely to have hundreds of accounts and passwords. And so the idea of these services provided by some big tech companies is that you only need one login, namely the login of that big tech company, or maybe two, and then you can use that to log into other web services. And by itself, that's great, right? Because you remember you should be rotating all your passwords from time to time, and you can bet I'm not doing this with my 250 passwords, right? So I'm not following all these security advice either. And if I had such one password that I just have to, only one password that I have to keep secure and updated every couple of months, that sounds doable in comparison to updating 250 passwords every 3 or 4 months. So that seems like a pretty good idea, right? Now let's look at the protocol a bit. So this is a very abstract picture. So it kind of works for both SAML and OpenID Connect, which are the two main protocols here. And the protocols roughly work as follows. First, you usually try to access the service provider. That's going to redirect you to the identity provider here shown by these logos. And you authenticate toward that identity provider with a password, or maybe you have an open session and authenticate by a cookie or some of these means. And then the identity provider is going to return something that is called an assertion or a ticket to your client device. And your client device then sends that assertion or ticket to the service provider or relying party, which may in the background do some additional communication with the identity provider, depending on the protocol, which then accepts or rejects this assertion or ticket that you've been sending. But there's a very critical point here, which is the only thing that binds your identity to what the service provider sees is trust in the identity provider. So the identity provider could, and I'm not saying that they're doing that, but they could, authenticate as you to all the services that you're using with that identity provider, which means there is a huge centralized trust, especially if those identity providers are used by large numbers of users. So while I do like the idea of only having one password, I really don't like the idea of putting all my accounts into the hands of one centralized provider. And now you can already imagine where I'm going to. Internet identity gives you a similar flavor of things, like there will be one protocol to manage your authentication needs. But it does so in a decentralized way. So there's one decentralized protocol that serves a similar purpose, but it's not relying on one service provider to do the right thing. It's a decentralized protocol, and only by participating in this decentralized protocol can you get such an assertion about your identity that you can use to log into services or to authenticate towards smart contracts in our case. So the following talk is structured in basically explaining some technical parts of internet identity based on how we use existing techniques, either from the web or the internet computer, and then finally putting it all together in the internet identity canister that serves the actual user experience. So the internet computer runs Canister smart contracts. Those are the little cans that you see on this cubicle internet computer here in this figure. And these canisters interact by what you can think about as RPC calls. So a canister can call a function with arguments on some other canister and then receive a response, a return value. Users interact with canisters on a technical level in very much the same way. So if you want to use a canister on the internet computer, what you do is that you specify a canister, you specify a function that you want to call on that canister, and then you specify arguments. In a bit more detail, what I've shown here on the left-hand side is an ingress message. So that contains of the contents of the message, which is effectively the RPC call, and an envelope, which handles the authentication. So the contents does, as I explained, contain the canister ID, the function name, and the parameters. It also contains the caller principal, which is the identity of the user. And the envelope contains the signature and the public key of the user and the signature that the user generated with the private key on the ingress message on this message I've shown here on the contents. And there's two things at the internet computer side that we have to check here. The first one is obvious, it's the signature, right? When the internet computer receives such a message from the user, what it does is it validates that the signature is valid for said content with respect to that public key. The second thing that we check is that the principal actually belongs to that public key. So the identity that you're seen as by a canister is actually an identifier. It's a principal or that we call a principal that is derived from the public key. So that's, in a nutshell, how authentication of messages on the internet computer works. Now I'm going to jump a bit to how web authentication works, not in the internet computer case, but in the general case, like in the two-factor authentication case on the web. And from there, I'll then go and explain how we're going to use, or how we are using web authentication on the internet computer. So the user flow, when you're logging into some website that supports two-factor authentication via web authentication, would be that you first authenticate via a username and a password. That tells the web server which user they should be expecting, and it will allow the web server to give you some hint, to give the user's computer some hint to be used with a secure element, with a secure token, in terms of specifying which public key to be used. But more importantly, what the server does is it sends a challenge. A challenge is just a random, I don't know, 30-something byte or so random string. It doesn't have any meaning, it's just a random string. And the user's end device will then, when running through the front-end steps that require this, the web authentication part, it will send the challenge to the user's secure element, which could be a USB thing or the trusted platform module in your computer, which is going to sign that challenge and send that back. So the response is just a signature on the challenge wrapped in a few like binary format things. And the user's computer then takes this response and sends it to the web server. The web server unpacks these encoding things and basically validates the signature. What I have not shown here is that there's a setup step, of course, in which the user generates the new key pair on the secure element and it registers the public key with the web server. That depends a bit on the particular service, but this authentication step is the one that is more important for us anyway. So how do we adapt this to the internet computer? Because there is no challenge, right? We can't have a challenge generated by a single web server. We have a protocol that we want to authenticate against, and that protocol may run on certain nodes, but the nodes can't really create such a like secret challenge type thing, right? It doesn't work. In a decentralized protocol, it's very hard to make such a challenge in a meaningful way. But if you look into web authentication, then what actually happens on the token is really only that the token generates a digital signature, which we've seen before, right? That's the only thing that we need for authenticating an ingress message is we need to generate a digital signature on that ingress message. So what we are then doing here is that we completely leave out the challenge part. It doesn't matter for us. We don't need any challenge from the server. Instead, what we do sign is the message itself. So we take the message itself as the challenge or the hash of the message, but that doesn't matter too much. And then we send the hash of the message to the secure element. When you like tickle your USB key or you provide your fingerprint to your sensor, whatever you need to do to invoke this signature mechanism, that hash of the message that your front end wants to send to the internet computer is signed. And your front end is then going to take that signature, pack it into the envelope of the ingress message, and send that off to the internet computer. The internet computer is going to validate that signature. And if that checks with respect to the mapping between the public key and the principal, and the public key, the message, and the signature, everything is good. It just works like a regular signature scheme for us. There's one more aspect that I want to go into here, and that is a delegation mechanism that we implemented. And I'll explain why we absolutely need it in a second. And the idea here is that you can have different cryptographic keys, and you can delegate capabilities from one cryptographic key to another. So what I've shown here on the slide is that the yellow key may be your long-term master whatever key. And then you use that key to delegate capabilities to the orange key, which may be a less persistent and more temporary key. And then you could even chain that and delegate from your orange key to the purple key on the right-hand side. So the idea here is that you could have keys, or you can have keys with different security properties, And then you create such delegations, which are usually temporary, in which you may be delegating capabilities from a more secure key to a less secure key, but subject to the expiration policy. So we actually do that in a lot when we use web authentication. When we use web authentication, the issue is that the user needs to be involved for every signature we generate. But usually there's multiple actions that the user wants to do. They want to, for example, log into the Internet Identity Management interface and then add a new device. And already here we have two messages. And so we don't want to ask the user for his interaction on every single message that we need to send to the internet computer. So what we do is that we generate a short-term key that we're never going to store anyway, just keep it in memory. We generate a delegation from the web authentication key to the temporary key, which is going to have a validity of just a few minutes. And then we use the temporary key for all the actual signatures. So that's one way of using the delegation, but it's going to be more important also going forward. The next ingredient that we're using is what we call canister signatures. And to explain what they are, I first want to dive a bit deeper into the internet computer compared to what I did before. What you probably all know is that the internet computer is actually not one monolithic block, but it does contain of many, many subnets, where each canister runs on some subnet. Each subnet can run multiple canisters depending on their load. It could be tens or hundreds or thousands of canisters on the same subnet. But the internet computer itself scales horizontally by adding more subnets and thereby adding more capacity to the internet computer itself. And what is now specific to the internet computer is that each of those subnets actually holds a digital signature key. It is, in this case, it's a key based on a scheme that is called BLS. It's a rather new scheme. It uses rather complicated math. It's rather slow, especially in verifying, but it does allow us a lot of things within the protocol. So what we do is we threshold share that secret key among all the nodes in the network. So all the nodes together, or rather 2/3 of the nodes working together, can create a digital signature that none of the nodes alone or any fraction with less than 2/3 of the network could be created. So only if the entire network, or at least 2/3 of the network, work together, can they generate such a digital signature. And that may seem kind of okay, interesting, but actually it's great, because what sets the internet computer apart from other blockchains here is that this allows a subnet to have a short certificate of validity of a certain piece of data. So if you think about typical blockchains, if you really, really want to know whether a transaction is actually valid, you need to download the entire chain on your device and validate the entire chain before you find that transaction. You need to recompute the state. That's the only way you can really, really be sure that what you're seeing is correct. The internet computer can create these signatures, like every subnet can create signatures with respect to the particular key hosted by the subnet, which means that clients can easily validate that a certain piece of data is actually valid and coming from the internet computer hosted on the subnet that the signature was generated on. And we're using that in multiple ways in the protocol. So one case is, for example, where the root subnet, which hosts the network nervous system, it does contain a directory that maps every subnet identifier to the public key of that subnet. So if you want to really know that the message that you received from a certain subnet actually came from the internet computer, what you need to do is you need to validate first the delegation from the root subnet to the subnet that sent you the message, and then you need to validate the signature from that subnet to you. So whatever the subnets are. Now, as I said before, we're building on BLS signatures, which are in the process of being standardized. So it's not some magic stuff that we came up with. It's actually a pretty cool scheme. It's mathematically super beautiful, but it's not as widely deployed as other signature schemes. And also, it's, as I said, it's more expensive in the validation, like a factor of a few hundreds more expensive than standard signature validations. And just a quick preview, we are in the Bitcoin bridging that we're going to implement, like the Bitcoin support on the internet computer, we are adding support for more standard signature schemes, which is going to be great because that is going to allow us to have a much tighter integration with existing internet infrastructure like certificate authorities, PKI, DNSSEC, all this type of thing is suddenly possible when we support these more standard signature schemes. Just as a slight preview, I'm really, really excited where we'll be moving. But anyway, let's go back to the signatures. Based on these signatures generated by the subnet, we define something that is kind of a pseudo signature for each canister. So the subnet can actually create a signature. The canister doesn't really have any secrets. A canister can only create a signature with the help of the subnet. So what we're doing here is that we define a pseudo signature scheme where the public key is not really a cryptographic public key. The public key is the canister ID and some auxiliary information that the canister can even decide. And the signature is the signature by the subnet that the canister is running on, together with some additional information that we need in order to validate the output of this, the canister. So in a nutshell, the subnet is not going to create a signature for every message that that any canister will want to sign in this way, but rather it's going to put them all into one big, what we call a Merkle tree. It's a hash tree, and then just sign the Merkle root. So the actual canister signature needs the verification of the subnet signature plus the verification of the Merkle tree. If that didn't make sense, not too bad. Just remember the canister signature schemes effectively allow a canister now to create a cryptographic signature. And the way we're going to use this is as follows. We have a canister that is the internet identity canister. It lives on the network nervous system subnet. And if a user wants to access any other canister, what we're going to do is the user's front end is going to generate a new session key, and then it's going to request the internet identity canister to provide a delegation on that session key, and it's going to send that back to the user. And now for whatever validity period the internet identity canister has set, the user can send requests to any subnet of the internet computer signed by the session key that are going to appear to the internet computer as coming from the principal that is related to the public key of the internet identity canister with the auxiliary information being related to that user. So the internet identity canister, you can think about it as generating one or actually multiple public keys for each user. And then using these, we can use these public keys that are user specific, but controlled by the internet identity canister. We can use those to derive user principals, meaning user identities, when we authenticate ingress messages to any other canister running on the internet computer. Now, pulling it all together, the internet identity canister has the main role of storing the user's public keys. So the user can have what we call an identity anchor. It's kind of the representation of all the data of that user in the internet identity canister. And the user can store multiple public keys associated with that identity anchor. That means the user could be storing a public key related to their computer, related to their phone, maybe one to their USB security key. Maybe they also have a backup option. I'm not going to go into detail there, but it could be another USB security key, or it could be a public key derived from a seed phrase. All these things are stored with the user's identity anchor in the internet identity canister. And the user will then be able to use any one of those public keys stored in the internet identity canister to authenticate with the internet identity canister, which will then, as explained before, create a delegation that will be useful for the user to use other canisters on the internet computer. So let's go through the entire flow. I've just taken Discover here as one example, one Canister smart contract that a user may want to access via their browser and may want to use a persistent identity served through the Internet Identity Protocol. So the first thing that happens is the user targets the Discover front-end Canister, which is going to load the initial front-end of Discover. And that's also going to display a button, something like login or sign in with Internet Identity. If the user does that, what happens locally is that the front-end code running in the user's browser is going to generate a new session key. That's the same thing I've explained on the previous slide. And it's additionally going to open a new tab in the user's browser, which is going to show Internet Identity. Now, there is some interaction between those two tabs going on. It's using HTML5 post-message communication. And which is just going to be used to, for example, communicate that public key from the Discover front end to the Internet Identity front end. The Internet Identity front end is then going to use one of the user's secure devices. I've used the USB security key here to request a delegation to that purple session key. And this request for the delegation is signed by the USB security key. The request goes to the Internet Identity Canister. The Internet Identity Canister then creates a delegation. Remember, that's a signed object stating that it wants to delegate to that session key. So it effectively signs that session key with this Canister signature scheme, returns that to the Internet Identity front end, which forwards it back to the Discover front end. And from then on, the Discover front end can use the session key to authenticate requests toward the Discover backend Canister. So that's how the protocol works on a high level. Finally, there's two things that kind of bit us when we deployed Internet Identity. The one that happened first was on the right-hand side, which was Apple devices tend to do their key management in a kind of peculiar way, which is if you delete your Safari browser history, they're just going to delete all those keys as well. And this is documented, and it's also kind of, Apple has a slightly different view on how they want to use web authentication, but it was still a bit surprising to us that they would actually delete those cryptographic keys. So this led to users effectively being locked out of their Internet identity. And so, which is when we upped our game on providing recovery mechanisms so that users, even if that would happen to them, would be able to recover their Internet identity at least. And there's nothing we can do here to solve that problem fundamentally, because the devices simply delete the keys. So there's nothing we can do about recovering the keys themselves. They have been the secure element, they have been securely deleted, they're just gone. And the next thing that kind of bit us was that Windows has this Windows Hello system for web authentication, which kind of works. It's just that it builds on really like ancient cryptography. It builds on RSA PKCS standards from like back in the 90s. And we initially didn't support that. So once we learned that we were actually preventing like these billions of Windows users from using Internet identity, we quickly went ahead, ported support for these ancient signatures to the Internet computer. And since then, we're also supporting Windows devices. Yeah, that's all I wanted to present today. So next, I'd then be very happy to take any questions you may have.
Cool. Thank you so much, Bjorn, for that. So we do have a lot of questions today, so let's see what we're able to get through. Okay, so Bjorn, first question, is the Internet identity the only way to authenticate into applications on the Internet computer?
No, it's absolutely not. It depends on what the Canister developer provides. So the Internet identity is one way of authenticating, and we try to make it easy for developers to use that. But there's also other methods, like there's the plug wallet that was built by Fleek, for example, that uses a kind of different philosophy in terms of how they manage the keys. And that can also be used. Like if it also needs, like internet identity, it needs some code in the actual canisters for the user to be able to just click the buttons on the web page. But that's another solution. And even if developers choose to support none of them, it's perfectly valid to just use a temporary key or to build your own solution in your own front end. Internet identity is really only a possible service because we think it's a good idea, and we'll see whether it's going to be picked up or in which scale it's going to be picked up, but it's by far not mandatory.
Great, thank you, Bjorn. And somebody in the chat said, I like your enthusiasm, Bjorn.
Thank you.
All right, so next question, and apologies, there's Fleet Week going on outside, so you might hear some planes flying ahead. How does internet identity solve the authorization problem for non-web authentication? So for example, can you use internet identity for mobile dApps?
So you can. The reason we require web authentication is for browser support. Like if we want to support browsers, there is not much we can do in terms of securely storing keys other than web authentication. I mean, there's web cryptography, which helps to some extent, but then it's not that great for keeping keys secure for a long term. So for the browser case, we were really only focused on web authentication, which means if you now try to use a browser that doesn't support web authentication, that's not going to work. But if you want to use specific mobile apps, for example, what you can do is you can generate an additional public key in that app and add that as an additional authentication mechanism to the user's identity anchor. And then the app can just request the delegation from the internet identity canister and get it returned. The API is fully open, so there's one call that you need to make in order to request and another call that you need to do to then actually retrieve the delegation. It's because signature generation is asynchronous, so we need to do this in 2 calls, but you can do that from an app. So there's no restriction in that sense.
Thank you, Bjorn. So next question, are there any plans to optimize the internet identity experience? It's several steps to be able to log in, so to speak, into a dApp with internet identity. And as contrast, if you're using single sign-on with Google, it's very quick.
Mm-hmm. There's some things, I mean, we are working on improving the user flow. We must admit that in some cases the user flow can really be improved. Also in terms of how we handle the devices in the UI, that's not as good as it probably should be for users to get in touch. Then with respect to the flow of just logging in, there is some kind of inherent delay, which is due to the generation of the threshold signature. So it's never going to be exactly as fast as sign in with Google, for example. That said, currently the internet identity is running on the main network nervous system subnet, which is also the biggest subnet, which also makes it the slowest subnet. And we expect that at some point internet identity is going to be moved to a different subnet for various reasons. And that may give a speed up because the block time and thereby the generation of those signatures could actually be faster on a different subnet. But it's never going to be exactly as fast as a centralized system.
Great, thank you. Bjorn, next question. Internet identity essentially leaves users relying on YubiKey or some biometric supported device. This lowers compatibility and ease of use for everyday or non-tech users. How does the team plan continued growth of the internet computer if you are relying on biometrics and physical security keys for access?
Mm-hmm. So this has 2 answers. The first one is we expect that web authentication support will be more and more will come more and more widely in consumer devices. Right now, it's more on the more high-end devices and less on the more low-end side. We expect that to change. But also there is some cases in specific countries where there are certain license restrictions, where things don't fully work. And there's multiple answers to this. So, or our thinking goes into multiple directions. And also it's very good to get your feedback on these. The first one is, if the user has one web authentication device, we could use that to online authorize other devices. Like if you have a phone, for example, which is quite likely to support web authentication, then for logging in on your computer, we could support just doing like scan one QR code and that's it. So this is one possibility that we could have for users that do have one device. There's also software solution for web authentication that work on devices that don't exactly support web authentication, but still have some kind of secure elements to them. And so these solutions could build the web authentication support itself based on software. We would need to rely on third-party tooling, however, that exists. It doesn't work with the internet computer right now for reasons we haven't looked into deep enough. But this is also another possibility that we could support additional software applications on some of the users' devices that may not exactly support web authentication.
Great, thank you, Björn. So next question is an interesting one. Do you have any plans on letting developers personalize or brand the UI for internet identity for their own applications?
I think that's not something we've been discussing so far. But again, I mean, if there's a desire for this, if that really improves the user experience, then we'd be happy to learn more. And I mean, it's an open project, right? We should be developing it together as a community, and we'll be happy to take such things into account.
I know Diego's on this call, so if that's something that we want to start a forum thread around, and if there's enough interest, we should definitely do so. So next question, we should have an option for a redirect-based authentication along with the pop-up-based authentication that internet identity currently has. A redirect-based authentication is less prone to browser-based restrictions on websites opening pop-ups and tabs. What are your thoughts around this, Björn?
That is actually difficult. So we started doing such a flow. We started with a flow that was much more based on OAuth than the flow we have right now. But that's actually less, like for the case of the internet computer, that's less secure. The reason is that for the mechanism we're using right now, where we have two pages run next to each other, we can use communication mechanisms that just work within the browser. And we don't need to trust anything except for the security mechanisms of the browser. If we do redirect-based solutions, then we run into the issue that we need to relay the requests through the internet computer itself, which kind of needs to make, where we would need to make additional trust assumptions. That can be solved to some extent, depending on how exactly we pass the parameters, but it still is kind of a leaky part of the system. So we're not really confident that we should be going back to such a solution where, like from a security perspective, the current solution just seems superior. That said, what we could be using is something that is based on an iframe, where you could just be embedding an iframe in a given page, and that iframe would run internet identity, and the frames could be using the same for communication. If that's another possibly helpful solution, I mean, please let us know what you think or what you need. Yeah.
Great, thank you, Björn. Next question. What kind of expanded support can we expect for internet identity going forward? Is there a public roadmap for internet identity, and can I contribute to development?
Well, first of all, the repository is open source. So, I mean, you can see things. I think you can do pull requests, if I'm not mistaken, although I think we did not have one yet. So I'm not 100% sure that you can. We do not have a public roadmap just for internet identity right now, because mostly because we're trying to triage different features, and we need developers that can do internet identity stuff, sometimes also for other features. So we have to see how we get these things all lined up. But generally what we aim to do is on a shorter time scale, improve user story, improve support for non-web authentication devices. So these things are on a shorter term roadmap. On a slightly longer term roadmap, we'd also like to improve the underlying protocol that does make some stronger trust assumptions than it would inherently need to do. So we would like to improve that as well, but that's more long-term timeframe.
Thanks, Bjorn. So I see some questions in the chat. So are there any plans on incorporating IPv8? It offers some features which could be useful.
Sorry, I think I didn't understand the...
So it says, are there any plans on incorporating IPv8, which I think has some features which could be useful? And if it's
interesting, I'll look it up. Okay. I can't answer that question, sorry, but yeah, thanks.
So if you
could be a great hint.
For the person who asked this question, if you want to clarify more, you're welcome to do so in the chat. Another question in the chat: would it be possible to build a component within some web framework like React, which could directly talk to the internet identity backend without going into an iframe or a new tab?
I mean, sure, you can, there's no restriction in what front ends can talk to the internet identity canister. Any front end can talk to the internet identity canister. It's just usually like the web authentication credentials that the user would generally generate when they use identity.ac0.app. They are scoped in the browser to that particular origin. So you wouldn't be able to use those exact credentials just from the security context of the browser. But other than that, there's no restriction. Any front end can send messages to internet identity. The reason that internet identity is secure is that we check the authentication on all the relevant messages when the canister receives them. So, but any front end could be sending them.
Great, thank you. So another question from the chat: can we support fixed principles to enable better Web3 experiences? So
this is a tricky question. The answer is we will be working toward this, but it does have pretty big security implications, which is why we want to be very careful. So let me quickly explain what those are. If you have a front end, like in my example, it was Discover, and that front end gets a delegation toward using the user's principal with backend canisters, then that front end can send any request to any canister. I mean, we can technically, the protocol supports us restricting the set of canisters that the delegation is valid for, but that's practically very difficult to do because your application may grow, you may add additional backend canisters, you may want to communicate with additional backend canisters. So doing this via the scoping on the canister ID is at least not trivial. And now if you have one front end that, for example, is you use in maybe it's the NNS step where you manage your ICP. And you have another front end that you just happen to use every now and then, and that's maybe a nice game or whatever. Then if we were just delegating the same identity to those two front ends, then the front end of the whatever game would be able to also interact in your name with the NNS step canister, with the ledger canister, and so forth. So that would certainly not be what is perfect from a security perspective. What we still think that we can be supporting eventually is that we have that configurable for the user, so that the user could decide that they have one principal that could be their high security principal. They only use it with the NNS step. And they could have another principal that they could be using with whatever social media apps where those apps could also be using the same data canisters or whatever, so that it's helpful to have the same principle. But so in short, we see that there's a utility we're just very conscious about the security implications because we do not want to build a giant security hole in the main internet identity.
Great, appreciate it, Bjorn. So there are a bunch of questions left, and I will try my best to get us through all of them by the end of the call. So question, could internet identity be used for other web applications that are not built on the internet computer?
Technically, yes, because all that we're using in the delegations is just effectively the origin of the canister. We scope to the origin of the canister, the origin of the website, which could be served from a canister or not. It's just that, as I said before, what we're doing here is we're authenticating ingress messages via public keys. And so what internet identity does, it is issues a delegation to a public key. So if you use internet identity from a standard web app, then the problem is that your web app ends up getting a BLS signed delegation to a certain public key. And you may be able to use that in the backend, but I think it's quite a bit of work to make your backend accept this as a means of authentication. So technically it's possible, but I guess it's a lot of work.
Thank you, Bjorn. Next question. Are there plans to have an internet identity management service to manage different internet identities under one umbrella?
So there's a plan of providing better support for users that, for example, have different security needs for different purposes. Right now, you can create different identity anchors, and maybe as a user use one identity anchor for more security critical things and the other one for less security critical things or so. But we're not really good right now in distinguishing, for example, between different types of authentication. So if you do web authentication, the standard would allow us to differentiate whether the user actually had to enter a PIN or use biometrics, or whether it's just touching a key. So which is effectively the difference between multiple factor authentication in one package versus single factor authentication, just you own the USB security device. So in that sense, where I want to get to is we will want to have more fine-grained security for the users. We have not yet decided on what will be the exact way in which we are going to integrate that into the system.
Okay, so two last questions. First question, why do we call it internet identity and not something more broadly understandable like username or single sign-on?
Yeah, that's a great question. I think I would have to relay that to the parts of Dfinity that made the name choice.
Okay, I was afraid you're going to relay that back to me. Yeah, that's an open topic. If people, honestly, I feel like if the community members feel strongly about like some kind of name change, definitely feel free to bring it up on our developer forum. So, last question: will my internet identity work with a VPN, under a different IP address?
Yeah, there's no restriction to IP addresses.
Okay, excellent. Well, looks like we still have a little bit more time, so I will tack on an additional question. What is spurring the growth of the internet identity anchors?
That's a good question. So I think the honest answer is there's two things. First of all, is actual users registering, but also there is what we expect that some of the anchors are actually not registered by users, but by bots. We don't know why. And we can't really tell who's doing that or why they're doing this, but just from looking a bit into the public data. So if you look into the API of internet identity, you can see which calls you can make publicly, and that will give you some information about identity anchors. And they just look awkwardly similar sometimes. So in that sense, we expect that there is not only like natural humans registering, but also some automated process.
Yeah, for sure. As someone mentioned in the chat, there's airdrops that are available through platforms like Discover. So people will try to register, multiple accounts to be able to try to qualify for an airdrop. Great. So that's all the time we have for today. Thank you so much, Bjorn, for that wonderful presentation and for being a good sport for all of these questions. Thank you to the community for all of your burning questions. Very spicy. Keep them coming. And see you guys all at a future community conversation. Bye, everyone. Take care.